Hello everyone. Today we are going to discuss the problem Planets and Kingdoms from CSES Graph problem set. Let's go through the problem. A game has n planets connected by m teleporters. Two planets A and B belong to the same kingdom exactly when there is a route both from A to B and from B to A. Your task is to determine for each planet its kingdom. So the input line has two integers n and m, the number of planets and teleporters. The planets are numbered from 1 to n. After then there are m lines describing the teleporters. So each line has two integers a and b. You can travel from planet A to planet B through a teleporter. So first of all you have to print an integer k, that is the number of kingdoms, and after this you have to print for each planet a kingdom label between 1 to k, and you can print any valid solution. So let's first of all try to understand what the problem is, and then we will see how we can actually solve this. So I have just redrawn the input example over here. So as you look, there is a teleporter from 1 to 2, 2 to 3, 3 to 1, 3 to 4 and 4 to 5. So in total there are 5 planets and there are 6 teleporters represented as edges. Okay, cool. So now over here if you look, if you start from planet 1, you can get teleported to any of this planet 2 or 3. If you start from 3, you can get teleported to any of this planet 2 and 1. Similarly, can I say that if I start from 4, I can get teleported to any of these planets 1, 2 or 3? No, right? So 4 and these nodes 1, 2 and 3 do not belong to the same kingdom. So if I just want to see the nodes in the same kingdom, so if you just look, nodes 1, 2 and 3 belong to the same kingdom, because if you start from any planet 1, 2 or 3, you will be able to get teleported to any other planet to this 1, 2 or 3, that is they belong to the same kingdom. Similarly, if you look, node 4, that is planet 4 and planet 5 again belong to the same kingdom, because if you start from any of these planet 4 or 5, you will be able to get teleported to any other planet in this particular kingdom. So there are in total 2 kingdoms over here. So the first part of the answer will be 2, that in total there are 2 kingdoms. And now if I just mark the kingdoms, let's mark all the planets in this first kingdom as 1 and the kingdoms for the another, and let the other kingdom be 2. So your answer will be 1 1 1 2 2. That is nodes 1, 2 and 3 belong to kingdom 1 and nodes 4 and 5 belong to kingdom 2. So I hope the problem is clear to each and every one of you. By a kingdom we mean that if let's suppose there are certain planets in a particular kingdom, so if you start from any planet, you should be able to get teleported to any other planet in that particular kingdom. Okay, now how we can actually solve this? So when I say this, that in a kingdom, if you choose your starting point as any planet, you should be able to visit any other planet. When we say that you should be able to get teleported to any other planet, what we mean? We mean that we should be able to visit any other planet in that kingdom, right? So don't you guys get the feeling that over here I am talking of a strongly connected component? I repeat, over here I am talking of a strongly connected component. Now, if any one of you don't know what do we mean by strongly connected component, or how do we actually find strongly connected component in a graph, so you should definitely check out the last solution in the list. That is, I think it was flight routes, some flight routes check was the name of the problem. You can just simply look to that, the solution for that particular problem. Over there, I have discussed this strongly connected components in detail. That is a slightly longer video. So if you want to understand how do we actually get strongly connected component, what is strongly connected component, what is the basic intuition behind the algorithm, so I have discussed everything in that particular video. So definitely I'm not going to repeat those things. Otherwise, again, it will make the video 45 minutes or 50 minutes long. But if you are watching the solution ahead, I just want a prerequisite that you should be able to know strongly connected component. If you don't know, and if you want to visit my particular solution, you can simply just check the solution of the last video. Okay, I will also try to attach the link for the solution of that video in this particular video as well, so you will be able to visit that. Cool. So I hope you guys now know what is strongly connected component. After that, you can see this particular solution. Okay, So over here, what I'm talking of strongly connected components, right? So this is one strongly connected component that I have, and this is the other strongly connected component that I have. So if you know how do we get strongly connected components, so you also know that we are able to get these components like this, vector of vector, and you will have all strongly connected components like this, 1, 2, 3, 4, 5. So now you have the strongly connected components with you, right? So now it's very easy for me to mark the labels. Let's suppose I mark all of these nodes as 1, then all of these nodes as 2. So this I can do via a simple for loop. So definitely there does not anything remains after knowing that what strongly connected component is. So the only thing that was left in this problem was to figure it out, that if you just separate the strongly connected components, you can mark all the nodes in that component by a single label and you will be good to go. So let's see the code for this for better understanding. For the ones who haven't watched my solution and they already knew the strongly connected component for before, for them I will just traverse this entire code once again. This is exactly the same code that I used earlier as well. Okay. So I'm taking inputs of nodes and the edges m, the graph and the reversed edges graph. So I'm basically using the Kosaraju's algorithm for the SCC, that is strongly connected component. Okay. Traveling over all the edges, taking the inputs of two nodes, converting to zero based indexing, pushed in the graph, pushed in the reversed edges graph. Then just finding a topo order, basically the order of decreasing order of T out time. So for that, I am just using a simple topo sort, the visited topo vector and the topo order vector, insert count as 0, going over all the nodes. If the node is not visited topo, that is in this particular DFS, I haven't visited that node, then doing a DFS from that node. Okay, in the DFS, simply marking the node as visited, going over all the adjacent node. If not visited, doing a DFS from there. Once done with the DFS for that particular node, inserting that node in the topo vector, and what will be the index at which it will be inserted? N minus insert count minus 1, because I am inserting from back, right? And increasing this insert count. So this insert count is basically passed by reference. Again, just repeating, watch the solution of the last video. You will be able to understand this pretty easily. Okay. Then finding the strongly connected components. So over here, I am just maintaining a visited SCC vector and the components vector and the representative nodes, basically one node from every component. Though we don't need it in this particular solution, but just because I have written the code of SCC as the whole, so I'm just keeping this as well. Okay. Going over all the node in the order of topo order vector. If the node is visited, just continue. If not, taking a vector in component, and in that particular component, keeping all the nodes that I am able to visit via this particular node. So in this DFS component, I am simply marking the node as visited, in the components pushing back that node, and if the node is not visited, doing a DFS from that. Once you are done with this, we are pretty much sure that in this vector of vector in components, I have the strongly connected components. So first of all, you need to print a number of kingdoms, right? So that will basically be the size of this components vector. After that, for every node, we have to label it as the kingdom, right? 1 to k. So initializing my count to 1, going over every component in this components vector, and in a particular component, going over every node, and answer of that node I am marking as count. Once I am done with a particular component, I am increasing the component number, or basically the count, by 1. So the other component will be marked by, let's suppose the first component is marked by label 1. So another component will be marked by label 2. The next component will be marked by label 3, and so on. So in this way, every component will be marked by some unique integer from 1 to k. K is basically the size of the components, basically the number of components that you have. Once you are done with this, going over the answer vector and printing the label for every node, and you will be good to go. So there was nothing much left in this particular problem. If you already know what is strongly connected component and how do you actually find this in the graph. So once you know that, this is a very, very easy solution question for you. Okay. I hope all of you understood it. Thank you.